we are at UiTM Kuala Pilar Reserve Forest.
And we are doing our field trip
to find interaction in ecosystem.
And we choose commensalism.
Interaction among population refers to the ways different group of organisms, either of the same species or different species, affect one another within an ecosystem. These interactions are essential for maintaining balance in nature. They can be helpful, harmful, or neutral depending on how the organisms are affected. There are two main types of population interaction. First, intraspecific interaction, which happens within the same species. For example, animals of the same kind may compete for food, territory, or mates. Second, interspecific interaction, which involve different species. These include predation, parasitism, mutualism, commensalism, and competition. This interaction help control population size, drive evolution, and shape the structure of ecosystem.
Commensalism is a type of biological interaction that occurs between two different species in an ecosystem, where one species gains a benefit while the other remains unaffected. This means that one organism receives something useful, such as support, protection, transportation, or access to resources without causing any positive or negative impact on the other organism involved. This relationship is important in ecosystem because it allows certain species to survive or thrive by making use of opportunities provided by others without creating competition, harm, or dependency. Commensalism helps maintain the diversity and complexity of ecosystem by allowing species to coexist peacefully without direct interaction that alters each other's health, behavior, or population size.
One simple example of commensalism in nature is when a hornet builds its nest on a tree. In this relationship, the hornet benefits because the tree provides a strong, elevated structure when the nest can be safely attached and protected from predators on the ground. The tree, on the other hand, is not affected in any significant way. It doesn't gain anything from the hornet, but it also doesn't get harmed. The hornet doesn't feed on a tree, damage it seriously, or interfere with its growth. So, in this situation, the hornet clearly benefits by gaining a place to live and raise its young, while the tree remains unaffected. This is the classic example of commensalism, where one species benefits and the other experiences no impact at all.
Another example of commensalism is when a climbing plant grows on another tree. In this interaction, the climbing plant benefits by using the taller tree as its support structure to reach more sunlight for photosynthesis. The tree that supports is not affected, it is not harmed, and it does not receive any benefit. The climbing plant does not take nutrients from the tree or damage its tissues. It simply climbs along its trunk or branches to grow upward. Because one organism benefits and the other is unaffected, this relationship is a good example of commensalism in nature.
For introduction of the experiment, this experiment aims to examine the variation in leaf dimension, including length, width, and weight, using basic statistical concepts such as mean, variance, and standard deviation. A total of 30 leaves were measured divided into 3 sets, with 10 leaves in each set. The main objective is to calculate and describe the descriptive statistic for leaf dimension and to explore the relationship between leaf length and width through a graph. The result of this experiment helped understand the natural variation in leaf characteristic and the use of statistical tools to quantify it. So the objective for the experiment is to understand the concept of correlation. Next is to calculate and describe the following descriptive statistic: mean, variance, and standard deviation. And the last one is to determine the relationship between the two variables. So the method for this experiment is each group were divided to take 3 sets of 10 leaves. For each leaf, it was measured the length and width, and the values were recorded carefully. Using this measurement from each set of 10 leaves, the 3 statistical parameters was calculated for length, width, and weight. The mean, average, the variance which show how spread out the measurement are, And the last one is the standard deviation, which indicate the typical deviation from the mean. This result was organized into a data matrix summarizing the mean, variance, and standard deviation for length and width across all four sets. Using this combined data, a graph of leaf length versus leaf width was plotted to visualize the relationship between these two variables. And finally, the graph was analyzed to determine if there was a relationship between leaf length and width.
Now we're going to the next part, post-lab questions. For the first question, discuss the differences or similarity of the mean of length between different set of leaves. Do the same for the mean of width. Your answer is, when looking at the mean leaf length across the three sets, we can see some differences. For set 1, the mean leaf length is 13.11 cm, while set 2 has a slightly higher mean of 14.69 cm, and set 3 exhibits the highest mean at 15.53 cm. This progressive increase in the mean value suggests that the samples in set 3 are on average longer than those in set 2 and set 1. The differences in the mean leaf lengths across the sets likely reflect natural variations in leaf size, which could be influenced by factors such as leaf age, plant species, or environmental conditions. As for the leaf width, set 1 has a mean of 5.89 cm, set 2 has a higher mean of 6.72 cm, and set 3 mean width is 6.14 cm. Like the leaf lengths, the width tends to increase from set 1 to set 2, but set 3 mean width is a bit smaller than set 2. These differences in leaf width could also be due to the same factors affecting leaf length, such as growth stage or environmental influences. In conclusion, while there is a general trend in the means of both leaf length and width, each set still demonstrate natural variation, highlighting the diversity within the leaf samples. Now for question 2. What is meant by variance? The leaf have different measurement of width and length. What is the meaning of this statement? Discuss with respect to variance what is meant by standard deviation. So now I will explain. The variance is a measure how much the data points differ from the average. It shows how spread out the measurements are. When we say that leaves have different measurement of width and length, it means that not all leaves are the same size. Some are bigger or smaller than the average. Variance helps us understand how far those measurements are from the mean. The bigger the variance, the more the measurement differ. Standard deviation is closely related to variance. It's just the square root of the variance, but it's in the same unit as the original data, which make it easier to understand. A higher standard deviation means the measurements are more spread out, and a lower one means they are closer to the average. In this case, both variance and standard deviation help us see how much the leaf size vary within each set of measurements. Now we're going for the last question. Why is it necessary to have different sets of measurements for the measurement of leaf width and length? So the answer is, it's important to have different set of measurements of leaf width and length because it helps us get a more accurate picture of the overall variation in the leaves. If we only measure one set, it might not reflect the full range of differences that exist in the whole sample. So using multiple sets gives us a better idea of how consistent or varied the measurements are across different leaves. It also helps reduce any errors or biases that might come from just using a single set of data, making the result more reliable.
In this study, we used the quadrat sampling method to estimate population size and density within a natural habitat. We established a 2 meter by 2 meter quadrat as our standard sampling unit. This size provided a manageable yet effective area for data collection. To reduce bias and ensure representative data, 4 quadrats were randomly placed throughout the habitat. Each quadrat was carefully observed. We recorded all visible species, identifying each one and counting the number of individuals present. This process was repeated across all 4 quadrats. Consistency in data collection helped us build a comprehensive dataset. We used the number of individuals recorded per species in each quadrat to estimate both population size and population density for the entire habitat.
the total number of individuals, we can get it by sum up number of individuals for each species. For density, we divide number of individuals for each species by total number of individuals and times 200, and we get the density in percentage. Okay, for the first postulate questions, define the term quadrat in practice. So a quadrat is a square frame used in ecological studies to sample and study plants in a specific or small area. It helps to estimate plant abundance, distribution and diversity by providing a standard unit for observation. So in this practice, quadrats are placed either randomly or systematically within a habitat, and all plant species within the frame are observed by counting individuals or species. So commonly use data collection on plant density, frequency and species richness. This method is simple, conserving and useful for monitoring changes in vegetation over time. Okay, for second question, what are the two basic requirements for all the quadrats technique? So first is random or representative placement. So quadrat must be placed randomly or systematically to ensure that the sample accurately represents the largest study area and avoid bias in the data. The second basic requirement in quadrat technique is uniform size and shape. So all quadrats used in a study must be of the same size and shape so that the data collected from each can be compared consistently and reliably across the area being studied.
When surveying sedentary organisms like plants or slow-moving invertebrates, using a smaller quadrat can have both benefits and drawbacks. First, the advantages. Smaller quadrats offer greater precision in dense areas. In habitats where organisms are packed closely together, a smaller quadrat allows for more accurate counts and detailed observation. They are also easier to handle and deploy, especially in rough terrain or tight spaces, making data collection quicker and more practical. However, there are also disadvantages. Smaller sampling areas may not represent the whole habitat well. This can lead to a limited view of the species present or how they are spread out. And there's a higher risk of sampling error. Rare or patchy species might be missed entirely, which could lead to inaccurate population estimates. Sampling in large forested areas or aquatic environments comes with several challenges. These issues can affect the accuracy of population estimates and ecological understanding. First, in accessibility and visibility. In habitats like dense forests or aquatic environments, many organisms are hidden from view or difficult to detect. This makes direct observation unreliable or impossible, forcing ecologists to rely on indirect methods such as acoustic monitoring, camera traps, or environmental DNA. Second, scale mismatch. The sampling area is often much smaller than the total habitat. If the sampling is not representative, it may fail to capture the true variability of the ecosystem. This can lead to bias or inaccurate estimates of population density. Sampling bias is another concern. If we only sample areas that are easy to reach, we may not get an accurate picture. Species might be clumped, evenly spread or randomly distributed, and poor sampling design can skew the results. Finally, time and resources. Large-scale studies need a lot of time, people and equipment. When resources are limited, we often take fewer samples, which lowers off the accuracy and statistical power of our findings.
As for discussion, this is the hypothesis that we made. Why is the difference in the number of plant species in the quadrat? So the number of plant species are different in quadrats is due to differences in environmental conditions, human activity and natural competition among species. So this is the factors causing variation in plant distribution across quadrats. First is soil condition. So nutrient level, pH, moisture and texture vary from place to place. So some plants thrive in richer or more acidic soils while others prefer dry or sandy areas. So next is light availability. So sunny areas have plants that need lots of light grow, while shady areas are better for plants that can live without less light. Trees or buildings can block sunlight, which affects how well plants grow in some quadrats. So next is water availability. So some plants need a lot of water while others can survive in dry soil. Next, the factor is human disturbance. So human agricultural activity can damage plants or compact the soil. So some quadrats might have fewer plant species because people step on them often. So the last factor is competition and plant interactions. Dominant species may outcompete others for space, light and nutrients, reducing diversity in some areas. So in other quadrats, resources may be more balanced, allowing more species to coexist.